To state the definition of the p-value mathematically, let big Y bar superscript act ACT denote the value of the sample average actually computed in the data set at hand, and let probability sub big H naught denote the probability computed under the null hypothesis, that is computed assuming that big E of big Y equals mu sub big Y naught. The p-value equals the probability big H sub naught, open bracket, the absolute value of big Y bar minus mu sub big Y naught is greater than the absolute value of big Y bar superscript act minus mu sub big Y naught. Close bracket equation 3.5. That is, the p-value is the area and the tails of the distribution of big Y bar under the null hypothesis beyond mu sub big Y naught plus or minus the absolute value of big Y bar superscript act minus mu sub big Y naught. If the p-value is large, then the observed value big Y bar superscript act is consistent with the null hypothesis. But if the p-value is small, it is not. To compute the p-value, it is necessary to know the sampling distribution of big Y bar under the null hypothesis. As discussed in section 2.6, when the sample size is small, this distribution is complicated. However, according to the central limit theorem, when the sample size is large, the sampling distribution of big Y bar is well approximated by a normal distribution. Under the null hypothesis, the mean of this normal distribution is mu sub big Y naught. So under the null hypothesis, big Y bar is distributed big N open mu sub big Y naught and sigma sub big Y squared close, where sigma sub big Y bar squared equals sigma sub big Y squared over N. This large sample normal approximation makes it possible to compute the p-value without needing to know the population distribution of big Y, as long as the sample size is large. The details of the calculation, however, depend on whether sigma sub big Y squared is known.